Welcome to CNC and CAM, and an introduction to modern CNC mill manufacturing. This is version 1 of this slide, and in the future I will hopefully update it and make it better. This is just a temporary image that I've chosen. Yes, let's go. This will be focused on milling. I will be mentioning like CNC turning, as like lathe work as well a little bit, but mostly it's going to be focused on CNC milling, on fler upp, as we would say in Swedish. I'm going to go through the basics of CNC and CAM, and there's going to be a lot of information, and I'm going to go through it pretty quickly. And as I said before, I think don't get too overwhelmed. Like, yes, it's going to be a lot of information, but I'm just trying to introduce the concepts basically. Okay, so CNC introduction. CNC stands for computer numeric control. When a CNC program follows code line by line, there's different types of code. The two big ones is ISO code, as it's called, and Heidenhain. ISO code is the standardized code that has G and M codes, as you may have heard. Whereas Heidenhain is a more specialized, or not special. It's a more sort of ISO code is very sort of simplistic and quite old, whereas Heidenhain is supposed to be a little bit more human readable. But it's a question of flavor basically. ISO code is easily the most common, but there's different types of ISO code, I will say. So like every machine, even though they both say ISO code, and it's supposed to be standardized, they can take, different types of code, you could say. The first type of coding is hand coding. So that's when you're doing it manually, completely like line by line. This is not very common anymore. With Heidenhain, it's quite common. That's sort of the way you do it. But with ISO code, like the most common, it's not so much common anymore, but it's quite handy to still be able to do a little bit, but it's not required. Another very common way of programming, just in general, is conversational. It's what it's called. It's konversationellt på svenska. One such system is, for example, Mazatrol. So that's developed by Mazak, which is a mill and lathe manufacturer. There, instead of manually coding and saying exactly where the machine is supposed to go, the machine essentially, or the system essentially asks you a bunch of questions like, what's the diameter, what's the thickness, like what's the contour, etc., etc., and then it on its own tries to figure out. But with a lot of these systems, and certainly Mazatrol, in the background, it's really ISO code. It's running on ISO code. It's just that it's creating a program for you, basically, in a really fancy way. The benefit of conversational is that it's really quick to change, because unlike ISO code, it can be fairly quick to create, but it can get really cumbersome to change a program because you need to change everything. Whereas on conversational, you change one line and it changes everything for you instantly. Yeah, and that's why I say in quotes, because it's like doing it in real time, basically. That's why it takes no time. CAM stands for computer aided machining. Another, like if you search for it, a lot of people abbreviate it as computer aided manufacturing. That's really common as well. I think that computer aided like manufacturing, machining is most applicable to what we do. So that's what I typically say. So we have CNC milling and we have CNC turning. Those are the most common, but CNC really can be applied to anything, computer controlled, basically, with this type of system. ISO programming, a little more in depth with that. So as I said, line by line, uses the G and M codes. So uses different types of codes, basically, like abbreviated short form, basically, for different functions. And I usually say a G code is basically go somewhere, so just go to some coordinate or whatever you want to do. And M is usually turn something on or off. There's exceptions to this, and they can sort of merge, but that's in general what you can do. And M basically stands for macro, and G doesn't really stand for something. But if you want to remember it, like go somewhere, G goes somewhere, M turns something on or off. All ISO machines and all ISO code is like all CNC manufacturing and machining is based around a coordinate system, of course. You have the first three axes, X, Y, and Z. And then if you have a fourth, fifth, or sixth axis, you would have ABC coordinate system. Another important thing is variables. So an M6 would be an M code. And then next to the M code, you can have a variable. So the variable would be T1. That's tool 1 in this case. Comments are common. So if you put a line with parentheses before and after, it will not run at all. It will just be ignored. So that's a comment. A common thing that I will probably say, and that's why I want to mention it now, because you will probably be confused if I say it. A program comment is a little more specific. So I'm going to get to it. The program number at the top of all programs, there needs to be an O code, and that's basically the identification of that program. And so for old school machines, you always need an O code. That's for well, it can be more, but most commonly 4 numbers. So begins at 0 and ends at 9,999. And that's basically the like sequence number, you could say. So usually program number 1 in a sequence is 1, and program number 2 in the sequence is 2, basically, right? But this is sort of an old school remnant, you could say. And like, for example, on Mazak machines, they've actually turned that into the article number, basically, which is, I think, is really clever. And so instead, if you had a part that's called TH1-001, that would be the O code, basically, you could say. But on old school machines, it needs to be, so typically you start at 1001, then 1002, that's most common. Then next to that, and that's why I wanted to mention it first, is the program comment. And so on old school machines, that would basically be your file name. And so you put the O code first, then the program comment. And so on the HAS, for example, what's in the first comment in the program, that will come up as the name, basically. So when you're camming in the setup, you will be asked of the program comment. And so that's basically the name. And you will be asked of the program number, and that's just a sequence number. Numbers under 1,000 are machine programs, is the way we do it. So user programs has to be 1,000 and over, but not over 9,000. So it's between 1,000 and 8,000, you could say. Otherwise, it doesn't matter. Other than that. So CNC ISO coordinate system. The way I usually remember it is I take my hand like this, as if I'm doing, I think it's magnetic fields or something. I do this, but I do it like that. And so right would be X, forward as depth would be Y, and then up is Z. I mention this because in a lot of CAD system, for example, Y will be up, but on CNC machines is almost always Z that is up. Yeah, so that's what I mentioned here. Almost always Z up, but it can differ sometimes. So next is CNC Work Coordinate System, often abbreviated as WCS. When So I sort of ask this question, why have more than one coordinate system? Because I think it would be very easy to think, okay, so the machine has this coordinate system. Why would we need more than one? Well, it's basically, we have this machine zero. If we wanted to use that for everything, it would be very cumbersome. Certainly, if you're hand coding, you would need to add whatever distance it is to your object all the time. That would be really annoying. So the idea with work coordinate systems is that you can define uh, more than like another work coordinate system that your piece is in. And so basically, this is the machine zero, so that's G53. This is G54, that's work offset 1. And then the next one, for example, would be G55, so that's work offset 2. And the reason for that again is that, like, let's say you have two pieces like this, then again, you don't need to offset for the one you already have. You can have two. And so if this one is perfect, but after you mill this one, you see it's a little offset, you can adjust just this one. You don't need to adjust both, of course. These are again called with the G codes. So G53 is read only, whereas G54 and G55 are read write, of course. These may sound complicated, but it's really simple. All it is, it's in the name, literally, it's a work offset. So all it's storing is how much you need to add or subtract from the machine zero, and that's all it stores in all axes, so X, Y, and Z, of course. I've illustrated the G53, the machine zero here for simplicity, but in reality it will be way here, because when the machine is zeroing, it's of course going as close to you as possible, like it's going all the way to the left and all the way forward. And so that would be the most negative coordinate, basically, it could go to, because no, I'm sorry, the most positive, rather. Yes, it's the most positive. Yeah, so it's going all the way there. But just for this illustration, it's right there. So another thing that I sort of need when people have cammed a lot of times, what I need to tell people, often people, because the question often comes up like, where do I put the origin of the part? A lot of people may think that that doesn't really matter, but it makes a big difference. A lot of people would let it remain in the default position, which I believe is in the center like this. This is fine, but we should keep in mind, the difficulty it may be when we actually machine the part, because of course the real world zero needs to be the same as in the CAM. And so if we put it here, we also need to, we need to probe this to get the zero. This would be a lot more difficult to get perfect in the center. We would need to take both edges in consideration to get it perfectly centered. So the next option would be this. So this is on the part edge. This is also not so easy because this is in the first stop, so we haven't machined any of these features yet. And so we don't have this edge to probe yet, of course. This I would say would be the easiest, of course, because you just take the left edge, take the top edge, and take the top. So this is best. This is also the least unprecise, because we're not taking into account any of the other edges, but for the first operation, doesn't really matter. We're just roughing, and every edge will be new, so to speak. So it doesn't really matter. It's best to just pick the easiest. I usually say, left is good because then you get positive x coordinates, and it's always best to put it furthest back. That's because this jaw is static, it will not move. And so it's often advantageous, you don't need to zero as often. Whereas if you put it here, this will change, of course. Yeah. Okay. CNC tool length compensation. So just the same as with work offsets, It's the same with tools. Tools will have different lengths. The CAM does not know the precise length of the tool. That is something we must put in the machine. And so that's the reason we need to compensate for tool length. In this illustration, we have, let's call it tool A. So this is a tool with this length. If a tool has a shorter length, we need to compensate for that. Also different lengths, of course. The G code for positive compensation is G43. And then again, we use a variable, so H, and then 1, 2, or depending on the tool. The T and H numbers does not necessarily need to match. Sort of traditionally or typically, you would have the same T as the H number because tool 1, H1, right? Makes sense. But the reason that we don't for our machine is that basically there are only 10 available tool spots in the machine, and it cannot store any more T numbers, but it can have up to 200 H numbers. So for that reason, all the H numbers that are permanent, that are always saved on the machines, those are above 10. So they start at 11 basically and then go up. But because of this, the T and H can no longer match, which is okay, but you just need to keep in mind that. A good thing that I think is a good rule is that any permanent tool will always have a number above 10, as I said. But any non-permanent tools, so that can be like a drill or tap that we often change, they will not. And so in those cases, it will be T5, H5, for example. And so that's a good way to sort of figure out what type of tool it is. Now we get to tool diameter compensation. And so this is again the same idea, but it's in diameter of the tool. This one has a lot of benefits, but in typical, when we're roughing with CAM, we're not using tool diameter compensation. And so the CAM is, of course, very, very easily just adding the radius of the tools for all roughing, and if you don't change it, even all finishing strategies. And so it will just offset all the time and just figures it out. It's very easy math, of course. But there are lots of benefits of diameter compensation. First of all, when we're manually programming, it's very, very beneficial, of course, because let's say in this example here, we have this tool. If we didn't have diameter compensation, as I said, we would always need to offset. Let's say this is 10, we would always need to offset by 5. Whereas if we used diameter compensation, we could just write essentially 0, 5 here, because 0 would be right on edge, right? It would be a cut of 0 millimeters. Yeah, this would be 0, 0, right? When we're doing tool diameter compensation for CAM, it's not quite as common as I said, but it's very, very useful for finishing passes because it's the same thing again with the tool length compensation that if we don't leave that in there, then we don't have that ability to adjust. And so for really precise surfaces where we need to adjust, and there can be a lot of cases of this, if we have tool diameter compensation activated, we can adjust for wear in the tool and basically compensate in until we have the precision that we need. G41 and G42, that's tool diameter compensation left or right. As I said, T does not necessarily have to be equal to H, but H is almost always, or no, I should probably rather say is always equal to D. If those are not equal, then something is wrong. Those need to be the same. Now we'll get to some G&M codes. I usually say that it's not necessary to memorize all of these. It's just good to keep in mind. Some are very, very handy and some is not so important. So G codes. G0 is a linear motion rapid in X, Y, and Z. G1 is a linear motion feed in X, Y, and Z, and then you also need to specify a feed. And so I think these are fairly clear. G0 basically go to some place as quick as possible, not precise, whereas G1 is a cutting motion basically, or a motion where you want to specify the speed. Yes. In between here is those are not so important to keep to remember, but I think G2 and G3 are circular interpolation, so that's cut a circle, cut a radii basically. G4 is dwell. So what does that mean? It means pause, because the CNC will always try to do all the commands as quickly as possible, of course. Sometimes you want the machine to stop. So G4 dwell is pause for a specified amount of seconds. And that one can go down to like milliseconds, I believe. And so that can be useful for a lot of cases. G43 is length compensation positive. G53 is machine 0. G54 till 59 is work offset. G90 and G91 is absolute or relative. What does this mean? It's does the machine move to absolute coordinates? So go to 100, go to 100, or does it add the amount you want to go to the position that you already are? So in some cases, it can be easy if you don't necessarily know where you are right now to just say, go 10 millimeter to the right, go 10 millimeter to the left. That can be very easily done with relative. What I usually say and why it's very relevant is that it can be a little bit dangerous to leave it in G91. So for that reason, in top of all programs, you always need a G90 because you don't know if it was in relative mode. And so you can easily cause a crash if it was in the wrong mode and you try to go, 100 millimeters down right into the table or something, Yeah. M codes. So M0, stop everything, stop the coolant, stop the machine, everything. And yeah, that's basically what it is. M1 is an optional stop. So if the optional stop is on when it reaches the M1, it will stop. If the option stop is not on the button, then it will just ignore and continue. M3, M4, spindle on. M5 is spindle stop. M6 is tool change. M8 and M9 is coolant off, on and off. And M30 is stop and return. So when it reaches the M30 at the bottom of the program, it will stop, but also go to the top of the program again. Yes, here comes a quick ISO programming example. And so this is the type of program you might commonly see that's hand-coded at least. You don't see that in the machine, but in the file, it needs to start with a percent sign. Then after that is the O code. Then we have the comment. So here I just retract. G53 is machine 0. Z0 on the machine 0 is retracted to the tool changer basically. And so that's a safe position, you could say. You do not know where the tool is at the beginning of a program, of course, so you need to make sure that it is where you think it is. After that, we do a tool change. The tool change automatically brings up the tool to do the tool change. And so you may ask, why do we need G0 or Z0 there? Well, the reason is that it might already have the T1 loaded. And if it did that, it would ignore the tool changer command and just continue, and that could cause a crash. And so we need to make sure both of these are true, that the right tool is in and that we are retracted. Then I load in the tool length for that tool, just for simplicity, H1. G54, go to tool offset 1. I'm sorry, work offset 1. M3 is 3000, turn on the spindle, 3000 RPM. M8, turn the coolant on. G0, rapid outside the part. Rapid down to about 200 millimeters above the surface of the part. G1, slowly go down to Z negative 1.0. That's because it moves very, very fast. So if you don't limit the speed, it will go very, very fast, and faster than you can stop, and that could cause a crash. So slowly. Then we feed to 100 millimeters. So that's cutting along the way, 100 millimeters at the feed of 300. And so you can see that G1 does not necessarily mean that we're cutting. In this case, I'm just slowly moving down at 500, and then we'll begin to cut. So 100 millimeters to the right. The feed is in millimeters per minute. What that is. Then we retract. We know that's safe, so that we can do that quickly. Then we move the table back towards door. Y0 is all the way to the front. And then M30, stop and return. Always ending with process time. Yes, now we get to CAM. So this is a CAM introduction. You may notice that the background is some toolpaths from CAM. CAM stands for computer-aided machining. There are lots of pros and cons of using CAM for manufacturing. The setup time, that's to say, like if you bring CAM to a company and start like from the beginning, it can be a lot of setup process to set everything up. It can be in some cases lower, but point is at the end, it's always quicker and more advanced in general, I would say, but there can definitely be pros and cons. Here at the university, we use HSM Works. So that's a system that Autodesk basically bought, and they've integrated into a bunch of their programs. You can still use it for SolidWorks, as I said, but works for Fusion and Inventor as well. There are other CAM packages like MasterCAM, but it's basically, again, different flavors of the same thing. The CAM pump line is basically as such. You CAD the part, you set up the part. That's where you define the work coordinate system, as I already said. This is also where you define the program comment and the O code and all things such as that. You have one setup per machine setup, you could say. So if you have two, like on the machine where you are milling the first side and then you flip it around and machine the other side, that will be two setups. After you set up the part, you use a variety of operations/strategies to rough and finish the part. And so in difference to when you're slicing for a 3D printer, for example, you're not just putting in some settings and clicking slice, basically. You're instead specifically specifying operations to clear different parts of the part and then to finish. Then after that, you post-process the program, and that creates the program for you, basically, with the ISO code. Next is common terminology. So there's a lot of words that I will say and they might confuse, and so I'm going to explain some of them. So first up, the part, that's essentially the thing that you want to machine, right? There's a stock, that's the beginning material that you want to machine, right? So it's the starting material. The fixture is the part locating and fastening. And so the vise can technically be called a fixture as well, of course, but it can be, custom-made fixtures for any part. WCS stands for work order system. Stock to leave. That is the amount of stock that you want to leave in a given roughing or even finishing operation. Sometimes roughing operations doesn't leave nice finishes, and so you might want to leave some material to cut away afterwards, and so that will be stock to leave. So that's the amount in millimeters you want to leave on each edge, basically. Because if you don't specify it, it will just machine off right to the edge. Optimal load is the optimum amount of the radii of the tool to apply in a roughing strategy. And so when you're roughing, you have the maximum depth, but you also have the maximum amount of the radii that you want to engage of the tool. I will get to that more later. Maximum roughing step down is the amount in Z that it's allowed to go down per pass, basically. And you can't go down more than you have end mill, basically, and so that's why it's an important variable. Smoothing is very it's applicable to all machines, but especially older machines. When the cam is doing especially circles and curves and stuff, it will often make curves into points, and so it will make lots and lots of points, you know, to interpolate a curve, basically. These amounts of, you know, millions of points can overwhelm the CNC and basically mean that it's going point to point and pausing on each point very slightly. But that means that in reality, you're not getting the specified feed that you want because it's doing like stops all the time, basically. And so what smoothing does is that it tries to apply curves to the points, basically, and it tries to minimize the amount of points that you have in your code. It's not detrimental at all to the finish of the part. The only consequence is that it can have longer calculation times. But the only times where I might turn it off is if it's a huge piece on the like wood CNC where it's just so much that it can like add another half hour or whatever. Usually it's only like seconds extra. Yes, I'm going to go through really quickly some of the terms and what the difference are between old versus new roughing strategies. So when you're doing side milling, you're cutting in both axial and radial. So axial is is called AP and radial is AE, basically. Those are the names for them. And so that is the amount that you're engaging in radial versus axial. When you're doing old school milling, you're usually DC is diameter. You're usually not going deeper than 1 times the diameter. So if this was a 10 millimeter end mill, you will not go deeper than 10 millimeters. If you're going a depth that is the diameter, that's considered quite deep, I would say. You're usually going fairly wide in radial, so you're going like half or 1 times the diameter of the tool in radial. You're going fairly slowly, and you're often more than 1 step down. So usually, especially for deep pockets, you have to do lots of axial step downs, right? When you're doing new school, that's often called high-speed machining, HSM. You're doing full depth of cut in axial. So in this case, you would do as much as you have flutes. You go as deep as you can. And this is, of course, assuming that the machine is strong enough, basically. So if you assume that the machine is as strong as you may possibly need, then you're doing full depth of cut in axial. You're doing, rather than doing full diameter, you're doing maybe usually 1/10 of the diameter. And so that would be the optimal load in this case. So you're only doing, if this is a 10 millimeter, you're only doing 1 millimeter in radial. And you're going way quicker. And so usually this is a lot quicker because you only do, you know, often 1 or like 2 step downs. And so instead of doing lots and lots of step downs very slowly, you're going a lot quicker. It's just that the cuts take a lot less. Yes, old version continued. Pocket is an older strategy, and you could perhaps call that an old style. It's a good finishing strategy though, and it's very fast in soft materials where you can, you know, go as much and quick as you want, and it can be smaller pockets. Truth is that more modern ones, they're just like when it's a slot basically, and it's exactly the width of the end mill, then you can't really do the modern stuff, and you have to go back to pocket and stuff. So that would look like this. So this is a pocket, a 2D pocket, as it were. And so you can see it's going rectangularly like this and milling out full diameter in this case, or slightly less actually, but almost full diameter. And so you can see in this case you needed to do 2 steps. Adaptive is what the operation is called for when you're doing the more modern high-speed machining type. This is a more modern strategy. It's faster in most cases, and it has high stability in harder materials. So that looks like this. So it has more of a spiral, and in this case, I'm actually doing 2 millimeter for a 10 millimeter end mill, just to speed it up mostly a little bit. But this is basically what it would look like. And so you can see per layer, yes, it can take longer. It doesn't necessarily have to be that way, because like especially when you compare, you know, new to old machines and really like expensive rigid machines to less rigid machines, you know, in this vacuum, in this simulation, it may seem like, oh, so the old style must be way quicker, like it finishes way quicker. Well, the truth is that because like our house, for example, it's so much weaker than so much less rigid and heavy than some like old really heavy machine would be, we would have to go so slowly to make up for the instability that the adaptive style would probably be quicker. Yes. 2D versus 3D real quickly. There are two types of operations basically, 2D and 3D. 2D, you basically select the model feature to cut. So you just say, cut this please, cut this please, finish this please, face this please, etc. So 2D adaptive is one such type, 2D pocket, 2D contour, bore, and such. So those are really common ones. 3D is basically select model features to not cut. So if you apply the 3D operation and you just press OK, it will try to machine everything. And that's almost always not ideal. So you almost always need to limit it and say, please don't machine here, etc. In a lot of cases, I think it's good to try to do 3D as much as you can, but in some cases, it can be so much of just selecting what you don't want that it's quicker to do a 2D. So 3D adaptive, 3D pocket, horizontal, parallel, those are really common ones. One thing that I mentioned here in the slide is to get approval for your CAM. I want that your CAD+CAM is okay and that the simulation is okay. So in Fusion, it will give you a verification. And so look that the verification is okay. Do that first. But also in Inventor, you just check that it doesn't crash, you know. Check the feeds and speeds for all the tools. Check that there are no overlapping tools. In a lot of cases, you can get like a TH1 and a TH1 that are different tools. You need to make sure that those are on different tool numbers. So in this case, this should be T2H12, for example. And so you need to go in and change that. And then lastly, check that the post is okay. And then you can send it to me for approval. And so the idea is that you send this to me and I approve it before we go to the machine. And this is to waste as little time as possible, basically, because what always happens is that people say, this is ready, I'm ready, this is finished, we can go and machine the part now. And we go to the machine and I look at the post and or at the code, I mean, and I see that, no, this will not work. Or what often happens is that I realize the problem in the middle of the machining process, and it's always like, I will just go and fix this quickly, and it takes 4 hours, it takes 6 hours, you know, and so I just don't have time for that. And so I approve the program first, and then we machine. Okay, that's it. Thank you for coming. You can scan the QR code, and that will lead you to the GitHub. You have not gone there yet.